So thank you, everyone, for being here today, and thanks also to the organizers for this opportunity to speak on behalf of the GPI 2.0 upgrade team. So I'm Quinn, like I said, I'm at UC San Diego, but you can see that there's a large collaboration of people that are working on the GPI 2.0 upgrade. Some of them drawn from the original GPI team, but also integrating some new students and postdocs and other collaborators as well to help bring this upgrade project to life. So I'm highlighting here in orange all the students and postdocs that are working on the project, and then yellow are the other people at UC San Diego, my team that's very wonderful, and I wanted to give them a shout out as well. Okay, so we have all of the scientific motivation that we need to describe the reasons behind the motivation for the GPI 2.0 project, but just to give you a sense, kind of an overarching sense of what this is. So what we envisioned is a system that we can take the existing GPI and refurbish it and upgrade it using some of the large numbers of advancements, particularly in technology, that have happened since the original design of GPI in the mid 2000s. So as you can imagine, in almost 20 years, there's been a lot of new developments that have happened. And part of the original plan with GPI was always to leave it on Gemini South for a while, and then after it kind of had finished its mission down there, to move it to Gemini North. And we thought, why not, upgrade it while that move is happening. So we've managed to raise funding for this project from a number of different sources: the National Science Foundation, MRI, the Heising-Simons Foundation, and NRC in Canada, all total $1 million for the upgraded project, which the PIs are Jeff Chilcote at Notre Dame and me. And then we have co-Is Bruce McIntosh at Stanford, who was the original GPI PI, and Dimitri Savransky at Cornell. There's the piece that's funded by NRC we're calling Cal 2.0 because it's an upgrade to GPI, but it's on a slightly different schedule. So that's led by Christian Marois at HAA in Victoria. For an overarching view of the timeline, so the design work is nearly finalized across all of the different pieces that we're going to upgrade. So I'll talk about those in a moment. GPI is in the process of starting its shipping. So it's going to be shipped to North America for the upgrade this fall. It'll be upgraded at Notre Dame in Indiana. Procurement of optics and hardware is mostly finalized, so we're waiting on some delivery. There's delays, as most people know, because of COVID on getting hardware. But we're working on the actual hardware implementation this fall into next year. And we want to be back on Sky at 2023 in Gemini North. So when we started, a few, maybe 3 or 4 years ago, to think about the idea that, GPI was finishing up what it was, its main mission on Gemini South, and we wanted to create this move to the north, what science did we want to enable when that transition happened, to think about what upgrades would be ideal. So, starting in about 2017, 2018, we started polling the scientific community, not only those interested in direct imaging of exoplanets and exoplanet science, which, debris disks and disk imaging in general are part of, but also people interested in other types of science that is not in the typical niche of GPI. So you can see here, we looked into things like looking at evolved stars, looking at asteroids and other solar system objects, and even pushing to nearby galaxies as well. And so from there, in polling the community, we got a sense of what types of requirements we would need to have on the instrument in terms of the type of stars it could observe. So right now, there's a limiting magnitude that our adaptive optics system internal to GPI can actually lock onto, an I-band that's about ninth-ish magnitude or so. And so how much fainter would we need to be able to observe to enable more science? How much closer would we need to go in terms of how we could probe close to the star? So we call that the inner working angle. And then how much more contrast would we need, or basically how much more sensitivity would we need to faint, structures like planets or disks or outflows, et cetera. So you can see that this table shows you kind of the summary of the results from that process. So I'm just going to go through a couple of the science results that we really hope are enabled by our upgrades based on kind of this gathering of data. So first, taking off from the planet piece, which is what Eric talked about. So the main lesson that we got out of the GPI1 survey, and also other surveys as well that have been going on at other facilities, is that we really need to get closer to the stars, and we really need to get fainter to be able to see fainter planets. So in comparison, so the results that Eric showed, in comparison to the scale of the solar system, and this is what he showed in graphs, but I'm showing it in a graphical form, is that most of the Jupiter gas giant-like planets are here, kind of in the exact range in our solar system where we found Jupiter and Saturn, so, the 3 to 10 AU range, or 1 to 10 AU. And there are very few Jupiters out here. So this is unfortunately exactly where we're primarily sensitive to with current GPI, just based on looking at the distances to the typical target stars, where we cut off in terms of our sensitivity. So we really need to get closer. And the other piece is, if we are actually observing stars or planets that have formed through core accretion, we also need to get fainter, which I'll talk about in just a second. So this is the closer piece. And so based on our notional improved understanding of the universe in terms of exoplanets, based on Eric's publication, we can make simulations of a notional universe that tell us the number of expected planets or brown dwarfs that form via this gravitational instability method versus those that form via core accretion. So those are also known as cold start. So core accretion start cold, and hot start are the gravitational instability ones. And so looking at this simulation that Eric did, he populated this pretend universe with these planets. And you can see where they lie in the distribution of separation in arc seconds versus contrast, or the difference in magnitude between the star and the planet. So this vast majority of the planets are kind of lying down here. And this is the lines of sensitivity from GPI1, a sampling of those. So even on our best nights where we're pushing down to the best contrast, we're going to miss the majority of these planets. So if we could get something that looks like this curve right here, the black curve, and push our contrast down, 2 magnitudes or so, we could easily pick up lots more planets that we think are now there. So that's one of the goals of GPI2. In addition, as Eric briefly mentioned, we do want to try to look at stars at a more wider variety of ages to probe for younger planets. And so another main science case driving the GPI 2.0 upgrade is imaging both protoplanets, so planets in the epoch of formation between 1 and 3 million years, and also looking at transitional disks where the planets are still forming. So the idea here was to look for nearby star forming regions that could be amenable to forming planets right now. So in the northern hemisphere, Taurus is kind of the prototypical example of this. It's about 140 parsecs away, and it's also really challenging to look at from the southern hemisphere. So what you can see here is, because typically planets are actually a lot brighter at this age range, because they still have a lot of gravitational potential energy that they're radiating. We're actually okay in terms of the brightness. So what you can see here is our contrast curve right here that we are hoping to get for a Taurus or an upper SCO target. And then where at about 1 to 3 million years, where a planet that mass would fall in terms of magnitude. So we could easily be sensitive to these types of planets if they exist. But the problem is that since Taurus is farther away and quite red since it's young, our limiting magnitude really hurts us here. So if we have only eye of 9th magnitude that we can lock on, or brighter, we don't have very many targets. So if we improve the limiting magnitude to 13th or 14th, we unlock greater than 50 targets we can observe in Taurus, and also about 24 transition disk host stars as well. Okay, and then additionally, just to go to one step further to think about other types of science that we can enable. So it turned out that a lot of times the GPI team would get emails from people interested in doing extragalactic work, particularly using the polarimetry mode of GPI and doing AO-assisted polarimetry. And unfortunately, with, again, the eye of 9th magnitude really limited people's ability to look outside of our galaxy. So if we could do this, if we could lock on to nearby AGN, AO-assisted polarimetry, it has a lot of really interesting applications for resolving, dusty toruses, outflow structures, magnetic fields, et cetera, of nearby AGN. So if we could get down to, again, 13th to 14th magnitude, there's potentially tens of sources that could be looked at. And so in this image, I'm just showing an example of some work that was done with SPHERE, which can actually target slightly fainter objects. So all of this led us to designing an upgrade path that could enable this type of science. So just to show you kind of the flow diagram that we often show for GPI, it's a very complicated instrument with lots of different modules or pieces that all work together to create these great images of exoplanets and other things. So first we have the Gemini telescope. The first place the light goes is to the adaptive optics system. So that consists of a wavefront sensor. So right now the wavefront sensor is a Shack-Hartman wavefront sensor that uses a Lincoln Labs CCD, designed circa 2008 or so. And there's also a real-time computer that runs as fast as it can to its abilities and controls the GPI deformable mirrors, et cetera, and provides the correction. From there, the light moves to the coronagraph, the APLC, Appetizer, Pupil Leo coronagraph. And so that blocks the light of the central star. From there, it moves to the calibration system, which does some lower order corrections and keeps the star aligned under the coronagraph. And finally, to the science camera, which is an integral field spectrograph. So it has low resolution spectroscopic capabilities in the near infrared and a Hawaii 2RG detector. We've spent a lot of time developing the data pipeline. And in addition to this, there's also the GPI top level software that connects to the observatory software and allows people to actually run the instrument. So for GPI2, what we're planning to change is everything highlighted in green. So you can see here we're getting we're designing and building a new wavefront sensor. So we're designing it to be a pyramid wavefront sensor rather than a Shack-Hartman with a brand new EMCCD. We're updating and getting a brand new, really, really fast computer to do the real-time control of the deformable mirror and other pieces of the AO system. We're updating a piece of the coronagraph with new shaped pupil appetizers. There's two different upgrades for the CAL. The baseline is to just upgrade the cameras inside of the CAL system with a CRED 2, which is a much more sensitive camera, so we can lock on fainter stars. And then in the integral field spectrograph, we're updating some of the prisms to have some new modes of observation, and just generally enhancing some of the optomechanicals pieces of the integral field spectrograph. Another main part of our upgrade is to enhance the top level software to enable much more efficient and robust observations at the observatory. So I'm going to talk through as much of this as I can before I run out of time. Okay, so first I'm going to talk about the pyramid wavefront sensor upgrade. So the nice part of the design for GPI is that it was actually, we were able to leverage a significant amount of research and development that has been done for TMT. So we heard about, how we can help facilitate the development of ELTs in the future. And I think GPI2 is going to be one of the main ways this happens, because we've come up with a design, and the design was done by HAA in Canada that is basically very, very similar to the design for Nefarious, which is the first light AO system for TMT. So this is an optical diagram showing the current AO path inside of GPI. This piece right here is the important piece. This is the current wavefront sensor leg. And what we're going to do is we have the space constraints here. We wanted to take advantage of reusing as much of the hardware as possible and not, buy things that didn't need to be upgraded. So we designed a pyramid wavefront sensor AO system that fits right into this little piece of the GPI larger AO bench. To show you what that looks like with a slightly more sophisticated CAD model, this is what it looks like. So you can see it has this interesting space shape envelope. So it's all going to be attached to a plate that's just going to lower down onto the current plate and be strapped locked on. And then you can see we just had to put in a few optics, so some fast steering mirrors, which are important for a pyramid wavefront sensor to modulate this incoming beam. A few new optics. This is the actual pyramid. So the nice part about the R&D in HAA is they figured out a vendor that could make a pyramid that wasn't nearly as difficult to build as some of the earlier pyramid wavefront sensor systems that were in existence. And then all of this goes to one of the main pieces that was important to upgrade, which is this new camera. So this is an EMCCD. These are basically zero read noise cameras. And the vendor that we've chosen for this is a relatively new player in this field called Nuvu. It's a Canadian company. And they figured out how to make an EMCCD that reads out faster than basically any other competing vendor. So the idea here is that we want to read out as fast as possible because that allows us to, perform our AO corrections as fast as possible, which then enhances the contrast that we can achieve. So we're really excited about this particular camera and this development. So just to show you one more picture, here's the view of a CAD model where we're going to plop this designed AO system down. In between, here's the MEMS deformable mirror. We're not going to touch that or break it, I promise. We have a very, very, very safe plan to get this in here. And it should just hopefully fit seamlessly into the existing AO system. So this piece, again, was designed by HAA with help from the Pyramid Wavefront Sensing team in Arcetri in Italy and some other people in Canada. And we're going to assemble this at UC San Diego and then deliver it to Notre Dame once it's finished. So we anticipate that our performance will be really much improved compared to GPI1. So here's just a couple of examples of some performance diagnostics that we did, some simulations with the current design. So this is the STREL predicted as a function of magnitude for different rates of running the AO system. You can see we have very, very high STRELs all the way out to 12th magnitude, and then kind of a slow degradation between 13th and 14th, but still achieving pretty good, sensitivity and performance. And the same thing is a function of scene. Okay, and then let's see, I want to talk a little bit about a couple other things. So as I mentioned, we have a new Appetizer going in. So there's been a ton of development work on Appetized people chronographs, often for space-based platforms, but also for the ground. So this is a diagram that shows you kind of the typical architecture, just a cartoon of a coronagraph of this type. So the first thing that it hits is an Appetizer that's in the pupil plane. It goes to a coronagraph mask, finally a LEO stop, and then onto the detector. So the only piece that we're changing is this Appetizer right here. So what you can see is that we have the original design for GPI only had 46% transmission. With the new optimized design, it has 76% transmission, and we anticipate a significant improvement in contrast just by changing this one piece. So those are on the way in terms of manufacture. I was missing my dots because I'm looking at a different place and I didn't see my stars coming in. So am I out of time? Yeah.
Yeah.
Okay. All right. Let me just mention one last thing really quickly.
Go ahead, please.
So I wanted to mention the AFIFS upgrade as well. Because people might be interested in this new mode that we wanted, which is this low resolution mode. And it's going to be a single shot YJHK mode. And so that's ideal for enhancing sensitivity and also for people interested in observing the entire infrared all in one shot. So you can see down here, this shows you will have the same kind of low spectral resolution for the individual infrared bands, and then kind of R of 11 for all this mode of 1 to 2.4 microns. So I'm sorry I have to skip to the end because I'm out of time, but here's what I wanted to summarize with, so I can stop talking and you all can just ask questions if you have any. Thanks.
Thanks, Quinn. We have 2 questions. One question was posted by Joel. Has the upgrade project been impacted by the jump in inflation, the cost-wise?
Yes, it has. So one of the things that's been noticeable is that glass is significantly more expensive. And so since we have, several optics that we're trying to procure, that's been a problem. It's, that's kind of the biggest one that I know of. Sometimes it's hard to tell, what's folded into costs in terms of, the inflation and like raw material costs versus the impact of COVID in general, and labor and just getting people to have time to work on it. That, labor rates, that's going up as well. So I would say, yes, we have been impacted by that.
Next question is posted by C. In terms of nighttime operation, would GPI 2.0 be pretty similar to GPI 1? Would the AO require a lot of fine tuning?
Okay, so I didn't get to show this. Thank you for that question, because now I can come back to this. So software is a huge part of what we're doing. So the real-time controller that's listed here for people interested, that it's going to be the same as the Gemini North AO algorithm. But one of the main things that we're really working on is this one button operations approach, because we know that the queue execution was lower than we had hoped and what everybody else had hoped, I think, as well. So we want to like get it to where it's not so finicky, and it's for any operator that's on, or any classical observer, it's like push a button and everything goes, and it's all easily executable. So that's a major piece of the upgrade, and significant amount of the funding too.
That sounds great. Next question is, what is the plan for the NRC CAL 2.0 upgrades?
That's a good question too. Thank you. Everybody knows my, they're like, you had to skip all these slides. Okay. I think, let me just show this one. So CAL 2.0, it's on a slightly different time scale. So this is, we're hoping to get this in place by late 2024. So a slightly longer time scale. But here's Christian Marois' kind of a cartoon diagram of the change. So the idea is that they're going to replace the current dual arm interferometer here by a common path interferometer. So kind of take this leg out and send all of the light just to a self-coherent camera. So there's a lot of nice things that come from this in terms of mitigating some issues with the current CAL, which have to do with vibrations. So it's hard to get it to give you the information that you want it to, because there's too much vibration. So since it's a common path, that won't be as much of a problem. And you can also do some interesting things. It does the sensing in the focal plane instead of the pupil plane, so that you can actually get science images from the self-coherent camera. And you can also do some interesting post-processing of speckles to hopefully achieve much higher contrast. So they're hoping, 100 times gain contrast with this upgrade. So a little bit longer term, but if you have more questions, you can check out Gerard 2019 or ask Christian Marois.
That was great. So I think that's all we have for Quinn's talk. And I'd like to thank every speaker of the day. And next 30 minutes, we have this separate chat session. So if you sign up for those different chat sessions, then please connect to those Zoom rooms. And after 30 minutes of this chat sessions, we have this MOS mask making workshop. So don't forget to come back to this main Zoom room. So I'll see you in 30 minutes.